Welcome to the second part of Module 4. In this part we will learn how to draw Lewis structures for compounds and how to use the VSEPR or VSEPR model to determine a compound's shape. The learning outcomes of the second part of Module 4 are: draw Lewis structures for molecules, identify the exceptions to the octet rule, and determine a compound's shape and polarity using the VSEPR model. We covered how to draw a Lewis structure for an atom and a molecule. Now we will cover the rules to draw Lewis structures for compounds while practicing the example of water at the same time. The first rule says, obtain the total number of valence electrons. You will need to add or subtract if writing for charged ions. In a water molecule, we have two hydrogen atoms. Each hydrogen has one valence electron. We also have an oxygen atom with 6 valence electrons, as it is in group 6A of the periodic table. So the total number of valence electrons in the molecule of water is 8. The second rule says, write the skeletal arrangement of the atoms and connect them with a single covalent bond. Use 1 dash to represent 2 bonding pair electrons. To do that, we usually have one atom in the center and the remaining atoms surrounding it. In our example, we put the oxygen in the center and the hydrogens around it. Most of the time, if not always, the hydrogen element is surrounding other atoms, as it can only make one bond. The oxygen is connected to the hydrogen with a single covalent bond. So we put 1 dash to represent this bond. The third rule says, calculate the remaining electrons. Remember that there are 2 electrons in each bond. This means we have used up 4 electrons so far, and we still have 4 valence electrons remaining. The fourth rule states, distribute the electrons to the atoms bonded to the central atom to meet the octet. That is, there's 8 electrons to give a noble gas structure. Hydrogen can only have 2 electrons. So in our example, the oxygen is the central atom and the hydrogens are surrounding it. So we distribute the electrons to the hydrogen first. Remember that we don't need to meet the octet rule for hydrogen, as it can only take up 2 electrons. Now because the hydrogens already have 2 electrons surrounding them from the covalent bond, then they are happy little atoms, and we don't need to add any more electrons to the hydrogens. The final rule says, place any leftover electrons on the central atom. If there are not enough electrons to give the central atom an octet, try multiple bonds by using 1 or more of the unshared pairs of electrons on the atoms bonded to the central atom to form double or triple bonds. As we mentioned in step 3, we have 4 electrons left, so we need to add them to the oxygen. Now, let's check each atom. The hydrogens are happy, as they have 2 electrons surrounding them. The oxygen achieved the octet rule, and it is also happy, and we have used up all the valence electrons, so we're happy. We will practice more examples in the coming slides and the tutorial session to master drawing Lewis structures. There are 3 general ways in which the octet rule breaks down. The first exceptions include molecules that have an odd number of valence electrons. For example, nitrogen monoxide has a total of 11 valence electrons, and there is no way to achieve the octet rule around both atoms. The next exception happens in some atoms that have less than an octet. Hydrogen is one example because of this exception. There are 2 additional examples of this exception, beryllium and boron. Beryllium is surrounded by 4 electrons, and boron is surrounded by 6 electrons. Examples of these molecules are beryllium chloride, and boron trifluoride. On the other hand, the last exception to the octet rule happens when some atoms can take more than 8 electrons. This is considered the most common exception. This exception happens in elements that have an energy level of n equals 3. The reason is that the d orbital becomes available and it can be used by the element to exceed the octet rule. For example, phosphorus, which is in energy level N3, can have 10 valence electrons in some molecules like PCl5. Nitrogen, which is on energy level 2, cannot exceed the octet rule as it doesn't have the d orbital. Now, we learned how to draw the Lewis structure for compounds, but it doesn't indicate anything regarding the shape or polarity of the molecule. Therefore, we will build upon Lewis structures and learn a new model called VSEPR, or VSEPR. This stands for Valence Shell Electron Pair Repulsion. The model is based on the idea that electron pairs will repel each other electrically and will seek to minimize this repulsion. So, the electron pairs will be arranged around a central atom as far apart as possible. This model will help us predict the shape and polarity of the compound. To draw molecules using this model, we need to go through some steps. The first step is to draw a Lewis structure for the molecule. Then, we need to count the electrons around the central atom, or the places that contain electrons around the central atom. So the central atom is the focus of this model. Those electrons tend to locate as far away as possible from each other to reduce the repulsion forces. Finally, we need to use an important table to work out the geometry of the molecule. This is the table you will need to learn in order to predict the shape of molecules. You can find it in your textbook on page 165. Please familiarize yourself with this table, as it will not be given to you in the exam. Let's practice the steps of this model using examples. The first example is to determine the molecular shape and polarity for a molecule of carbon dioxide. First, we need to draw the Lewis structure for this molecule. Carbon has 4 valence electrons. Oxygen has 6 valence electrons. So, there are a total of 16 valence electrons. We put the carbon in the center and bind it to the 2 oxygens. So far, we have used 4 electrons. Now, achieve the octet rule on the surrounding atoms, oxygens in this example. To do that, you need 6 electrons around each oxygen. Let's calculate how many electrons we used and how many are left. We used 4 electrons to make the bonds, and then we used 12 to achieve the octet rule on each oxygen. So we have used up all our valence electrons. Now let's check the carbon. We only have 4 electrons. According to the final rule of Lewis structures, if there are not enough electrons to achieve the octet rule on the central atom, we must try multiple bonds. So let's bring one pair of electrons from around the oxygen and make it a double bond. When we check again, we have an octet around the oxygen, but we only have 6 electrons around the carbon. Thus, we bring another pair of electrons from the other oxygen to make another double bond. When we check again, we can see that we have achieved the octet rule around all the atoms. Now we move to the second step of the VSEPR model. So we need to work out how many places that contain electrons around the carbon. Please note that double and triple bonds are also counted as one place. So in our example, there are 2 places where the electrons are available. To do steps 3 and 4, we need to check the table. The first column is the number of electron pairs, and we discussed that this means how many places contain electrons around the central atom. So in our example, we had 2. This means that the electron pair arrangement for our molecule is linear, which means a straight line. In the linear arrangement, the bond angle between the pairs of electrons is 180 degrees. The fourth column in the table refers to how many bonds there are between the central atom and the surrounding atoms. Again, double and triple bonds are counted as one bond. In our example, we have 2 bonds as carbon is connected to 2 oxygens. So the molecular structure is also linear. Now, let's examine the polarity of the compound. Oxygen is more electronegative than carbon, so it will pull electrons towards it. This will create the partial negative charge on the oxygen and the partial positive charge on the carbon. So we have polar covalent bonds. However, the important question is whether the whole molecule is polar or nonpolar. To answer this question, let's use the following analogy. If we think of the molecule as a tug of war, the oxygen is pulling the electrons towards it on one side, and the other oxygen is pulling the electrons towards it. Because they are the same element, they will have the same pulling strength, so they cancel each other out and the carbon atom will not move. When the central atom doesn't move, this means that the compound is nonpolar. So, overall, the molecule of carbon dioxide is nonpolar. This is an illustration of carbon dioxide, and you can see that all 3 atoms are on a straight line, so the geometry is linear. The second example is to determine the molecular shape and polarity for HCN. Let's start with the Lewis structure. Hydrogen has 1 valence electron, carbon has 4, and nitrogen has 5. So in total, we have 10 valence electrons. The central atom in this molecule is carbon, and it binds to both the hydrogen and the nitrogen. So we have used 4 electrons so far. Now it's time to achieve the octet rule on the surrounding atoms. Hydrogen is happy with 2 electrons. Nitrogen has 2, so it needs another 6 electrons to achieve the octet. Let's check the carbon. It only has 4. So we need to make a double bond between the nitrogen and the carbon. Check again, and the carbon has only 6. So we make a triple bond between the nitrogen and the carbon. And now we have an octet around the carbon. Now we use the VSEPR model. Count the places of electrons around the central atom. We have electrons between the hydrogen and the carbon, and we also have electrons between the nitrogen and the carbon. Remember that the triple bond is counted as 1 place. So in total, we have 2 places of electrons. From the table we see the electron pair arrangement is linear and the bond angle is 180 degrees. The number of bonds is 2 because the carbon is bonded to the hydrogen and the nitrogen. So the molecular structure is linear. Let's determine if the molecule is polar or nonpolar. Nitrogen is more electronegative than carbon, so it will pull the electrons towards it. Hydrogen and carbon have very close electronegative values, so if we think of the tug-of-war analogy, we have the nitrogen pulling the carbon from one side, the other side is not pulling at all, so the carbon is going to move to the direction of nitrogen. So when the central atom moves, we say that the compound is polar. This means that the molecule is polar. From the illustration, you can see that HCN is a linear molecule. The third example is to determine the molecular shape and polarity for the BF3 molecule. First, the Lewis structure. Boron has 3 valence electrons, fluorine has 7 valence electrons. So in total we have 3 plus 7 plus 7 plus 7, which is equal to 24 valence electrons. We put the boron in the center and the fluorines around it. We have 3 bonds, so that's 6 electrons. We needed 18 electrons to achieve the octet on the surrounding fluoride atoms. So we don't have any more electrons. However, the boron has 6 electrons around it. Remember, the boron is one of the exceptions to the octet rule, and it only needs 6 electrons around it. Now, let's check the table to determine the geometry of the molecule. Let's count how many places of electrons there are around the central atom. We have 3 places of electrons. We also have 3 bonds. So from the table we can see that when we have 3 electron pairs, the arrangement is trigonal planar, and the bond angle is 120 degrees. As we have 3 bonds, then the molecular structure is trigonal planar. Trigonal means the molecule has the shape of a triangle, and planar means the molecule is flat and all the atoms are on the same plane. In terms of the molecule's polarity, fluorine has the highest electronegative value in the periodic table, so it pulls the electrons towards it. However, the molecule is not polar because the fluorine in each side is pulling using the same force, so the boron will not move. From the illustration you can see that BF3 has the shape of a triangle and it is flat, so all atoms are on the same plane. The fourth example is to determine the molecular shape and polarity for HCHO molecule, or formaldehyde. The total number of valence electrons for this molecule is 1 plus 4 plus 1 plus 6, which is equal to 12 valence electrons. In this molecule it might be tricky to determine the central atom. Hydrogen can only have 1 bond, so it never gets the central position. Oxygen can form 2 bonds, and carbon can form 4 bonds. So we'll put the carbon as the central atom. As the carbon is connected to 2 hydrogens and the oxygen, then we need 6 valence electrons. There are 6 remaining. Both hydrogens are happy with 2 electrons. To achieve the octet rule for the oxygen, we need 6 electrons. This means we have no electrons left. Let's now check the carbon. It has 6 electrons, so we need to bring 1 pair from around the oxygen to make a double bond with the carbon. Now let's check how many places of electrons we have around the central atom. We have 3 places, and the number of bonds is also 3. From the table, the molecular structure is trigonal planar. In terms of polarity, we have the oxygen pulling electrons towards it. The hydrogen is not applying any force to the carbon, so the molecule is polar. From the illustration you can see that formaldehyde has the shape of a triangle, and it is flat, so all atoms are on the same plane. The next example is to determine the molecular shape and polarity for the methane molecule, CH4. The number of valence electrons is 1 plus 1 plus 1 plus 1 plus 4, 8. Carbon is the central atom and is bonded to the 4 hydrogens, so that's 8 electrons used up. Hydrogens have 2 electrons each, so they're happy. Carbon has 8 as well, so it's happy too. There are 4 places of electrons around the carbon. Looking at the table, we see the electron pair arrangement is tetrahedral, and the bond angle is 109.5 degrees. There are also 4 bonds, so the molecular structure is also tetrahedral. the molecule is nonpolar. In terms of drawing the tetrahedral structure, we can use dashes and wedges to present the 3D nature of the molecule. The dashes represent that the atom is going away from you, and the wedges mean that the atom is coming towards you. From the illustration, you can see that CH4 has the 3D structure with atoms coming towards you and others going away from you. The next example is to determine the molecular shape and polarity for the CH2Cl2 molecule. Draw the Lewis structure by yourself, and it should look like this. So we have 4 places of electrons and 4 bonds, so both the arrangement and geometry are tetrahedral. Because the chlorine has a higher electronegative value than carbon and hydrogen, then the molecule is polar. From the illustration, you can see that CH2Cl2 has a 3D structure with atoms coming towards you and others going away from you. Another example is to determine the molecular shape and polarity for NH3, or ammonia molecule. Draw the Lewis structure by yourself, and it should look like this. We have 4 places of electrons, so the arrangement is tetrahedral. However, one place is a lone pair of electrons, as there is no bond between the central atom and a surrounding atom. So there are only 3 bonds around the nitrogen. This means that the molecular structure is trigonal pyramidal. The difference between the trigonal planar and pyramidal is that in the planar, the molecule is flat and all atoms are on one plane. However, pyramidal means that the molecule has a 3D structure with atoms going away from you or coming towards you. Therefore, we use the dashes and the wedges to draw the 3D structure of the molecule, similar to what we did in the tetrahedral structure. The lone pair of electrons is very important as it has an effect on the shape and polarity of the molecule. In terms of polarity, ammonia is a polar molecule, as the lone pair of electrons will exert an effect on the nitrogen and the nitrogen will move. From the illustration, you can see that the ammonia has a 3D structure with atoms coming towards you and others going away from you. Compare this structure to the trigonal planar from previous examples. The final and most important example we will cover today is water. Remember the Lewis structure of water. There are 4 places of electrons around the oxygen, so it has an electron pair arrangement of tetrahedral. There are only 2 bonding pairs of electrons, so the molecular structure is bent. The bond angle is 109.5 degrees. The shape of the water molecule looks like this. In terms of polarity, the oxygen has a higher electronegative value than hydrogen, so the water molecule is polar. From the illustration, you can see the bent structure of the water molecule. Here is the table to determine the shape of the molecules again. Notice that when we have the same number of electron pairs and bonds, then the electron pair arrangement is similar to the molecular structure. This applies to the first 3 rows of the table. Remember, you need to memorize this table to predict the molecular shape in the exam. This is the end of Module 4. We will summarize the key points from the module in the following few slides. In the first part of Module 4, we covered 2 chemical bonds, namely ionic and covalent. An ionic bond happens as a result of electron transfer from one atom to another atom. Ionic bonds happen in ionic compounds. On the other hand, in the covalent bond, there is a sharing of electrons between the two atoms. This happens as a result of orbitals overlapping between the two elements. Covalent bonds happen in molecular compounds. After that, we discussed the concept of electronegativity and stated that elements have different abilities to attract electrons, as can be seen from the electronegativity table. Fluorine has the highest value compared to the other elements, and as we move away from the fluorine, the electronegativity value starts to decrease. So if the difference in electronegativity between two elements is 0 or close to 0, then we expect to find a non-polar covalent bond. If the difference in electronegativity is close to 1.5 to 1.7, then we expect to find polar covalent bonds. In this type of bond, one element will get a partial negative charge and the other a partial positive charge. When the difference in electronegativity approaches 2, the bond will be ionic. We also covered Lewis structures for atoms, molecules, and compounds. So to draw a Lewis structure for an atom, we write the atom symbol and place the valence electrons around it. Take boron as an example. In molecules, we do similar steps and place pairs of electrons to represent the covalent bond. We said that we can draw a dash instead of the shared electrons to represent the bond. 2 dashes indicates double bonding, and 3 dashes indicates a triple bond. After that, we learned how to draw a Lewis structure for a compound, and we covered the example of water. In the last part of Module 4, we learned how to determine the shape and polarity of compounds using the VSEPR model. So when there are 2 pairs of electrons and 2 bonds, the compound will be linear. Carbon dioxide was our example. If the compound has 3 pairs of electrons and 3 bonds, then the structure will be trigonal planar, like BF3. If the compound has 4 pairs of electrons and 4 bonds, then the structure will be tetrahedral, like methane, CH4. If the compound has 4 pairs of electrons and 3 bonds, then the structure will be trigonal pyramidal, and we covered the example of ammonia. If the example has 4 pairs of electrons, 2 bonds, then the structure will be bent, and the example for this compound is water. This is the end of Module 4. Please practice the weekly exercises in your textbook and the questions you find in your workbook. We will meet face-to-face in the tutorial session, and this will be your opportunity to ask any questions or to seek clarification of any topic.